Hello students, this is a presentation on the quiz exams as well as on the homework problem. See that this is the first question about the assumption of the preferences, and it is straightforward that if continuity is missing, then it will not be possible for us to draw the indifference curves. It rules out the lexicographic preferences, as well as it ensures that the indifference curves are not having holes in them, and so continuity is the correct answer for the first question. Then see that out of the commodity bundle x by which one of for sure cannot be on the same indifference curves. So you needed to compare these different bundles. See that if we compare option A with option C, so what is happening is that consumption of X increases, consumption of Y decreases, and so there is a possibility that they might be on the same indifference curve. Similarly, when we are in D, again we observe that 6 is less than 8, so one of the common good is decreasing in consumption, the other one is increasing in consumption, so this again is a possibility that these 2 points might be on the same indifference curves. And similarly is true about the option D, because we move from 6 to 3, consumption of X decreases, 6 to 10, consumption of Y increases. So in each of these 4 bundles we see that one of the consumption is going down and the other one is going up. But if you look into B, you know that 10 is greater than 7 and 6 is greater than 5, and this means that compared to A, both these commodities are having more quantities, and so this means that the commodity bundle B should be on a higher indifference curve. Similarly, see that 10 is greater than 8, 6 is greater than 3. Again, comparing C and B, B should be on a higher indifference curve. Similarly, 10 is greater than 6, and while I am having 6 here, so there is also again a possibility that this bundle might be offering a higher utility, and same is true about the comparison here, because in this case as well. So B actually is the bundle which is probably on a higher indifference curve. So 7, 5, 8, 3, 6, 6 and 3, 10 can be on the same indifference curve, but this is definitely not true 10, 6 when we compare 10, 6 with 7, 5 or 8, 3 or even 6, 6. Then the third question is that if the Marshall demand function for a good X is like 15 and rate minus 1.3 px minus 1.8 py plus 3m, then we know that on price elasticity, this is not wrong, this is not correct, because elasticity formula requires that dava x over dava p times p by x. So this is the own price elasticity formula, and see that if we look into the first option, so this is only dx by dp, so this cannot be the own price elasticity. And similarly, when we look into the second option, that goods x and y are substitutes to each other, this is something that is not true as well, because if we take the derivative of x with respect to price of y, then we find that it is equal to minus 1.8, and this means that in fact two goods are complements, and so goods x and good y are complements. So this is the answer to the third question rather. Then we have the adding up property of the demand function requires that Martian demand function may satisfy budget constraint, at all prices and income, so that if you have income equal to price of x into x plus price of y into y, so this actually means that if we plug into this budget constraint the margin and demand function, then for all prices this right hand side should be equal to left hand side. This is what that adding a property is. So A is the correct answer. Then we have this fifth question. In a two commodity world, suppose that you know that on price elasticity of one of the good is -1, then you can infer that two goods are substitutes to each other, two goods are complements to each other. Cross price elasticity of the other good is equal to 0. See that this is something that we had seen in class, the Carnot aggregation, and if we put on price elasticity equal to 0, so this becomes equal to 0, and when on price elasticity of good one is -1, so this becomes equal to -1. So if this becomes -1, then this means that this will be minus alpha 1 here, and on the right hand side of this equation we have minus alpha 1, so alpha 1 gets cancelled, and we will have alpha 2 cross price elasticity of good 1 with respect to 2 is equal to 0, and this will give us epsilon 1 2 equal to 0, so cross price elasticity will become equal to 0 from because of Carnot aggregation. So this is something that is true. And then we have question 6. This is the indirect utility function that we had derived for the Cobb-Douglas utility function u equals to x raised to the power 0.5 and y raised to the power 0.5, and we know that in this case the Martian demand curve for x is equal to m divided by 2px, and given this means that this cannot be the answer. Similarly, this cannot be the answer for the reason that income is not an argument in the action demand function. Similarly, we cannot say that x is an inferior good, because if we take the derivative of x with respect to m, so it is equal to 1 over 2p, which is greater than 0. So this means x is a normal good, so this cannot be the case. Similarly, at price of good 1 equal to 10 and income of the household equal to 1200, the household consumes 75 units of good 1. This is also not correct. You can plug this, these values here, so you will find that x is not equal to 75. So the correct answer is none of the above. Then is the seventh question. Suppose that in two good world we know that the household spent 20% of income on a good that has income elasticity of 1.2. So here we make use of the Engel's aggregation. This is the formula that we had seen in class, and that what we are saying is that one of the commodities having an income is having a spending share equal to 20%. So 0.2 is the spending share and 1.2 is the income elasticity, and because one of the good is having an income share of 0.2, then this means that other should be having an income share of 0.8, and so we get 0.24 equal to 0.8 multiplied by income elasticity of the second good, and when we solve this we get 0.95, and so this is the correct answer. Similarly, in a two good world, both goods are necessarily complements. Both goods are necessary cross complement. This is incorrect for the reason that in a two good world there is a possibility that good might be cross complement or cross substitutes depending upon the total effect, cross effect in fact. Similarly, both goods are necessarily cross substitutes. This is also not necessarily true. In fact, in a two commodity world, we only know that both goods are net substitutes, and so this means that E is the correct answer because that is the option that is not available here. So E is the correct answer. In a two commodity world, we know with surety that two goods are net substitutes. Now, the concavity of the expenditure function is implied by the optimizing behavior. This is something that we had seen in the class. It is straightforward that when, for example, the consumption of when prices are increasing, expenditures will be increasing at a decreasing rate. It's for this reason that the option C is the correct one. Then Slutsky equation implies that action demand curves always have a non-positive slope because substitution effect is non-positive. So this means that the slope of the action demand curve must be either less than 0 or equal to 0, but it cannot be positive. So this is the correct answer for equation 10. Similarly, see that in the second quiz, the first question was like when average total cost is equal to 50, average variable cost is equal to 30, and then side by side the other information was given was about the total fixed cost, it was equal to 100, and then it was asked that we know that the firm is producing how many units. So see that we know that average total cost minus average fixed cost actually is equal to, sorry, my average very average total cost minus average variable cost is equal to average fixed cost, and average total cost is equal to 50, average variable cost is equal to 30, and average fixed cost has not been given, but total fixed cost has been given equal to 1000. So average fixed cost actually is equal to total fixed cost divided by output. So this is the definition of average fixed cost. And so see that we have one variable here, and so we have in this case 20 Q equal to 1000, and this gives us Q equal to 50. So correct answer is equal to 50. Then the second question is that at an output level, if at an output level it was observed that average total costs were equal to 125 and marginal costs were 100. So this means that marginal cost is less than average total cost, and whenever marginal cost is less than average total cost, then this means that average cost is falling. So if output increases, average total cost will fall. So this is the correct answer for question 2. And then we have increasing returns to scale implies that long run average cost is downward sloping. This is something that we had seen in class, that in the long run average cost is like this, and this is like saying that when all the inputs are increasing, total costs are increasing at a decreasing rate, and that is something that is causing the average total cost to have a downward sloping. So long run average cost is downward sloping. This is something that we had done using the example where we had that this was isocon and isocost, and then we had doubled the um, the inputs, and then we had this isocon, and this was equal to Q, and if this is greater than 2Q, so then this means that average total cost will be falling, and so B is the answer. Then we have, if we assume price taking behavior in the input and output market, then we know that the profit maximizing employment of labor is, in price taking behavior, we know that price times marginal product of labor actually is equal to wage rate is the condition which ensures profit maximizing employment of labor. So value of marginal product of labor is equal to market wage rate, that which is this condition, and so D is the correct answer. Then we have let the production function be L raised to power 0.7, K raised to power 0.7. We know that this production function is increasing returns to scale. Returns to scale is increasing because if we define Q star equals to lambda times L raised to power 0.7, lambda let it be greater than 1, and so capital also is increased by the same proportion, and then we will have Q star like equal to um, lambda raised to power 1.4 uh, Q, and this is something that is like saying that output will be increasing more than the increase in the proportionate increase in the factors of production, and so the returns to scales are increasing. But side by side, if we take the partial derivative of this with respect to L, so it will be equal to zero point 0.7 multiplied by L raised to power zero point 0.7 minus 1 equal to zero point 0.3, and K raised to power zero point 0.7, and this is marginal product of labor. And then if we take the second derivative, dou I square over dou L square, so it will be negative because this minus zero point 0.3 will be coming down, so we will be having minus 0.21 L raised to power minus 1.3 and K raised to 1.3 and K raised to power 0.7, and this is negative. So this means marginal product of labor is diminishing. The increasing rate of return and marginal product of labor and is diminishing. Same is true with marginal product of capital. You first take the derivative of this function with respect to k, and then take the second derivative, and the second derivative will be less than 0, and that is something that will imply that marginal product of capital is diminishing. So both margin products are diminishing, and this is something that tells you that even with increasing returns to scale, there is a possibility that marginal product of any of the factor of production might be decreasing. Not necessary, but it could be the case. Then we have an increase in the employment of capital. When capital increases, you see that shifts the total product of labor curve. This is something that we know because this is the total product of labor curve, and if this is the total product of labor curve, it is like for a particular quantity of capital. So capital is being kept constant. If capital increases, so this total product of labor curve will be shifting upward, and with total product of labor curve shifting upward means marginal product and average product of labor curve will also be shifting upward. So answer E is the correct answer. Then we have this this is a direct question number 7. This is directly coming from the variant text, that if the input requirement set is such that x1 is in input requirement set, that is x1 can produce q level of output, and then we have another input vector such that that input vector is not less than the first input vector, then we should be able to produce at least q units of output. So that is something that is telling us that the technology is monotonic, and so this is something that is defining the correct answer. Which one of the following is not true for profit function? See that profit function is convex in output prices, and it is also convex in input prices. So if I am having an output price here and profit function here, which is a function of P and W, and see that the profit increases like this, and this again is coming directly from the lecture that we had in our class. Similarly, if W is the wage rate, for example, and we have profit function P and W, and this profit function will be falling like this. Profit will be decreasing at a decreasing rate, And again, these trends are because of the optimizing behavior. So that is something that you need to keep in mind. Right, then we have question number 9, which is like saying that which one of the following is not true of the cost function? Non-decreasing in price. Remember that when we were like trying to obtain the cost function, see that that was something we were doing in the factors of production space, and in the factor of production space we had where is that question? Uh, yeah, it is. We had this isocost and isoquant, and so I see that cost functions were associated with these tangency points, and because we have labor around here and capital, and then side by side we have W over R. So see that there is no mention of output price. So because cost function has not does not have output price as its explanatory variable, so this means that this has nothing to do, output price has nothing to do with the cost function, so this is not a property of the cost function. And then we have this 10th one, that when two goods X and Y are produced using both labor and capital such that each unit of X requires 150 units of labor and each unit of Y requires 40 units of labor, only then we know that X is labor intensive, this is wrong, capital intensive, this is wrong, and similarly total product of labor is flatter, all this is wrong, we cannot say anything about that, and so none of the above is true. So these are the 10 questions of the second quiz. Then we have this homework problem. The first one requires you to draw the indifference curves of given preferences. So see that household likes, the first one, A, is household likes to consume X, so that when household consume X, utility increases, but Y gives him or her no utility, so that neither utility increases or decreases. This is like saying that Y is neutral to consumption of Y is neutral to utility, and in this case indifference curves become vertical. So see that if you, like for example, increase consumption of Y, say in this direction, you keep on moving along the same indifference curve, so your utility does not increase. Similarly, if you go down, again your utility does not decrease, so increased consumption of Y or decreased consumption of Y has no effect upon utility. But if you increase consumption of X with constant amount of Y, so see that you move from one indifference curve to a higher indifference curve, which suggests that indifference curves are vertical. Then we have B, that household cannot survive if consumption of X and Y falls below X naught and Y naught. So I have like this like survival constraint. So if you are consuming less than Y of good Y, so you will not be surviving, and if you are consuming less than of good X naught, you will not be surviving. So this means that you should be in this range. So this is because if you are on this, like for example here, you are consuming X less than X naught, so you won't be able to survive. If you are here, you will be consuming less than Y naught of good Y, you won't be surviving. If you are consuming here, you will be consuming less of y less than Y naught and X less than X naught. Again, you won't be able to survive. So your indifference curve should be satisfying these survival constraints. And so this is something that is the shape of the indifference curve. The indifference curves will be lying in this range. So you can keep on extending um, these boundaries, and you can keep on extending these graphs, but definitely your indifference curve will not be crossing this limit. So this line, neither this vertical line nor they will be crossing this horizontal line, because you won't be able to survive. Then we have C, and that C is saying for every increase in X, quantity of Y must increase by an amount greater than the increase in X, so that y, this is something that is happening here. Y is like increasing at an increasing rate, and when this is the case, then if you recall that income and substitution factor screencast, you will be able to understand that this is the case which is saying x is bad and y is good. So this is the correct figure for C. Then, like saying that after y naught and x naught, mm, each good becomes bad. So see that we have a normal and difference curve up till y naught and x naught, but as we move up, y naught, see that y becomes bad. So this is the case where good y is bad, and this is the case when good x is bad. So see that in this range good x is bad, and in this range good y is bad, because we increase the consumption of y with constant consumption of x. We move from a higher to a lower and to a lower indifference curve. Similarly, see that if you are in this quadrant, what is happening is that if you are increasing the consumption of any of the goods, so your utility is decreasing, you are moving from a higher to a lower indifference curve. So indifference curves are like circular, with this point as the bliss point where the person attains the highest utility, and more consumption either in this direction or in this direction or in this direction decreases the utility of the person. So this is the answer to D. Then, for every cup of coffee, the household consumes only half teaspoon of sugar. This is the case of perfect complements, and so see that 1 cup of coffee, half cup of sugar, 2 cup of coffee, and 1 cup of sugar, and so on. So you are able to get Leontief type indifference curves, perfect complements, and this is the relevant utility function for that. Alright, then find the marginal demand functions for the following utility functions and verify their properties. So see that as far as this utility function is concerned, it is known as a Stone-Gary utility function, and this is the utility function which actually is having the indifference curves like this one. Here we have like y naught units of y and x naught units of x. So if you look into this utility function, this is something like this, and in order to maximize utility subject to the budget constraint, you need to write down this Lagrangian function, and then you write down the first order condition. So I have written down these three first order conditions by taking the partial derivative of the Lagrangian function with respect to x, with respect to with respect to y. And this is with respect to y, and then with respect to lambda, and then we solve 1 and 2 to get this equation, and from here we arrive at py times y minus y bar equal to px times x minus x bar. Then I have opened these brackets, py minus py times y bar equal to pxx minus pxx bar, and then I take this py bar on the right hand side. So I have py on the left hand side, and see that I could have solved this equation for y, and if I had done that, I could have obtained the Martian in demand function for y, but I did something else, see, and it is that once I had obtained this equation, see that I plugged this py in the third equation. Here is in this third equation to satisfy the constraint. So m equal to pxx plus, in place of py I have put this equation, and from here then I get pxx plus pxx equals to 2pxx minus px bar plus py bar, and so on. See here, this is what that I was telling you, that I could solve this equation for x, and this would be the marginal demand function. But then I wanted to write it a little bit in a cleaner way. And so see that what I have done here is that m plus px x bar minus py y bar. So this is all this thing, and then I have added px x bar and subtracted px x bar, so nothing has changed. When I do this, so see that I have px x bar here, px x bar here, and so I get 2 px x bar, and so I have here 2 px x bar in this equation. And then see that from here I can write this equation as 2 pxx bar. So pxx bar equal to 2 pxx bar come here. This 1 px bar x bar is left, and this is coming here, and then py y bar is coming here, and so I get x equal to x bar plus half of m minus px x bar minus py y bar divided by p rather. So I have missed p of x here, p of x here, as well as p of x here. Similarly, p of y here and p of y here. So this is the why I have written it in this format. Well, the reason is that see that this is like saying that let me correct it. There is a little bit of correction. First, let me correct it a little bit. This is like see that there is a typo here. I need to remove it. So this is the actual equation, and I divide this equation by 2px. When I divide this equation by 2px, so I get x bar here, and I get half of 2px here, half of 2. Let me do it in the next equation here. Let me do it correctly. Alright, so that confusion is not here. So see that let us there's so much noise. Alright, see that this is the equation that I have. This was the equation, and I had 2px here. I took this px bar and py bar on the other side. So this px bar become plus, and this became minus. Now this is what that I have done. This is your equation, this one, and then I have added into it plus pxx bar and minus pxx bar, so nothing changes. And when I do this, so I get 2 px x equal to m plus this pxx bar, and this pxx bar becomes 2 pxx bar, 2 px bar. Now I am left with this minus pxx bar minus px x bar, and this minus py y bar. So minus py y bar, and then I rearrange it a little bit. 2px x equal to 2 px x bar plus m minus px x bar minus py y bar, and I put this in bracket, and then I solve it for x. So x is equal to x bar plus 1 over 2 px m minus px x bar minus py y bar. And similarly, y will become equal to y bar plus half of py m minus px x bar minus py y bar. And see that this equation is giving us a message. If you look into these terms, so because x bar and y bar could be seen as subsistent quantities, what this is saying is that from M you subtract the subsistence expenditures, and then only you will be able to find the value of y or the value of x. The value of x is equal to x bar, the subsistent quantity of x, plus 1 over 2 px times m, whatever is the income, minus the overall subsistence expenditures. So this is one thing. And remember that if we did not have this survival constraint or subsistence level of x bar and x and y in terms of x bar and y bar, so that x bar would have been equal to 0 and y bar would have been equal to 0, then this utility function actually would have become u equal to x raised to power 0.5, y raised to power 0.5, which was like the Cobb-Douglas utility function, and then you will be having x equal to Marshall demand function for x equal to m divided by 2 of px. But once you have put these survival constraints or subsistence amount of x and y, so see that what is the result implication is that now I have the demand function as x bar plus 1 over 2 py times m minus, let me write this thing in bracket, px x bar plus py y bar. And now you should be able to understand that this is your subsistence expenditure, income minus subsistence expenditure. Put x bar and y bar equal to 0, you will be able to get this thing. So this is Stone-Gary utility function actually is sort of a variation of the Cobb-Douglas utility function with the variation in terms of survival constraint that the person should at least be able to consume x bar units of good x and y bar units of good y. And this utility function actually is used a lot in welfare studies. So this is the part A for the Stone-Gary utility function. Now look into this second utility function, u equal to minimum of 3x over 2y, whichever is minimum. So just for the sake of your understanding, suppose that the person was consuming 2 units of x and 3 units of y. So let's say 2 units of x and 1 unit of y. So x equal to minimum 3 times 2 units of x and 2y, say 1 unit of y. This will be u equal to minimum of 6 and 2. So which is the minimum of 6 and 2? Minimum is 2. So this means that we will say that utility is equal to 2. The utility will be read in terms of the minimum of these two numbers. If suppose that we increase the consumption of y from 1 to 2, so this will become 4 and your utility will become equal to 4. And if we increase the consumption of y to 3, so we will have 6 here as well as 6 here, and this means that minimum will be 6 because both of them are equal. Now the other thing that you need to remember is that the Lagrangian method could only be applied if the function is twice differentiable at least, and this is something that is not the case with this utility function, and so we have to solve for the market and demand curve in a little bit different manner, and so see that this is what that I have done. First thing that you should remember is that um, that you make utility same. So first, in order to solve this equation for Marshalian function, first equate these quantities which are in the parentheses. So 3x equal to 2y, and from here you can get x equal to 2y over 3. Once you have obtained this result, then you will be putting the value of x in the budget constraint, and when you have done that, so then you will be able to get the value of x and value of y. So you do not apply Marshalian demand function, remember. Whenever you are given a utility function, u equal to minimum, let's just write it in a little bit general form. Say u equal to minimum of alpha x or beta y. So what is the way of finding the Marshalian demand function for this utility function? First, equate alpha x equal to alpha y, and this is something that will actually be giving you this ray at which is coming from the origin, and at which you will find these corners aligned along this ray. So we first need to find this ray, and this is what that we have done. So if in place of solving for x, suppose that I had to solve for it for y, so it will be like y equal to 3 over 2 x, and see that we are plotting y here and x here. The y is equal to 3 over x, means that whatever is the y, and we will be having this slope equal to 3 over 2. So this slope is equal to 3 over 2. See, y over x is this vertical distance is y, this horizontal distance is x, and so y divided by x is equal to 3 over 2. Y divided by x is equal to 3 over 2 is the slope of this line which is going here, and on this line are these corners of these different curves. So once you have obtained either y equal to 3 over 2x or x equal to 3 over 2y, the next step is to plug this or this quantity into the budget constraint, and once you have done that, then you can solve for the value of x as well as the value of y. So this is the way you will be solving this utility maximization problem, and then you will be able to see that this is going to be the Martian demand curve for x and Martian demand curve for y. Do they satisfy homogeneity and von Laws law? The answer is yes. See that if if you multiply m and prices by lambda, so your x will remain unchanged, because you will be getting lambda here, you will be getting lambda here, you will be getting lambda here, and then lambdas will be cancelling out. Similarly, is true about y. Similarly, if you put this utility function in the budget constraint demand function in the budget constraints pxx plus pyy equal to m, then see that px is here, and then in the bracket x is your 2m divided by 3 of px, this is your x, plus 2 of py. So this is py. This is your px times x plus py times y. So I have py times y. Y is equal to 3m over 3px plus 2py. And when you do this, you'll see that the LCM will be 3px plus 2py, and here I will be having 2m times px plus 3m times py. You can take m common, and when you take m common, you will be left with 2px plus 3py, and in the new denominator, you have 2px plus 3py here, 2px plus 3py here, 2px plus 3py here, 2px plus 3py here, and when you take it in 2px plus 3py, uh, so 2px plus 3py gets cancelled and you are left with m, and so we have left hand side equal to right hand side, m equal to m. So the budget constraint is satisfied. This is true for Valverde. This is like linear indifference curve. So see that if you take the total differential of this equation, it is 3 dx plus 2 dy, and from here you can find out dy by dx equal to minus 3 over 2, which is the marginal rate of substitution between x and y. And so see that I have drawn these indifference curves which are having slope equal to minus 3 over 2. Now again you will not be using the Lagrangian multiplier. See that you have to look into three possibilities. The first possibility is that the price ratio is greater than 3 over 2. Price ratio is greater than over 3 over 2 means that the budget constraint is steeper than the indifference curve. And this budget constraint is steeper than the indifference curve, and see that where you get your utility maximized. When you move up along this indifference curve, see along this budget constraint, see your utility keeps on increasing, and ultimately you arrive here. The maximum utility you are able to get here. So this means that whenever this is the case, you will not consume only y. Because you will consume only y, so this means x will be equal to 0. And because you are spending all of your income on consumption of good y, this intercept actually is the intercept of the budget constraint m over py. Similarly, this is the intercept m over px. So see that you maximize utility only on this corner. So this is the corner solution that you will be getting, y equal to m over py. This is something that will be happening when px over py is greater than 3 over 2. What if px over py is less than 3 over 2? If px over py is less than 3 over 2 means budget constraint is flatter than the indifference curve, and see that you will not be maximizing your utility here or here or here. Your maximum attainable utility level is at this point, but at this point you are spending all of your income on consumption of good x, and so this is your consumption of good x. X is equal to m over px. So if px over py is less than 3 over 2, then this means that x will be equal to m over px. You will not consume any unit of good y, so good y will become equal to 0. What if px over py is equal to 3 over 2? Then in that case, the budget constraint actually will be completely coinciding with the indifference curve, and so you can have any solution for y as well for x between 0 and m over py and 0 and m over px. So see that this is what that I have written here along this point. Um, Let me, it takes a little bit time to move down. Yeah, ज़्यादा नीचे चला गया. Yes, here. Px over py equal to 3 over 2. So x can be anything between 0 and m over px. You can consume here, you can consume here. Your utility level is maximum here as well as here, as well as here. So you can consume m over px units of good x, or lesser or lesser or lesser along this constraint, to the extent that you could arrive here. And so this could be the consumption point. So the consumption of x could be between anything between 0 and m over px. Similarly, consumption of y could be anything between 0 and m over py. So let's write down the conditions for the demand function. This is what that I have done for Martian demand function for x. 0 if price of x is greater than 3 over 2 py, and this is like saying that px over py is greater than 3 over 2. Similarly, it is equal to m over px if price of x is less than 3 over 2 py. This is the case that we had seen where px over py is less than 3 over 2, and it is anything between 0 and m over px if price of x is equal to 3 over 2 py, which is like saying that px over py actually is equal to 3 over 2. And similarly is about ym. I have written that px is less than 3 over 2 py. So see that px is less than 3 over 2 py, because whenever px is less than 3 over 2 py, you are spending all of your income on consumption of good x. So this means consumption of good y should be equal to 0. M over px is greater than 3 over 2 py. So px is greater than 3 over 2 py means consumption of x is equal to 0, and see that in that case you are consuming spending all of your income on consumption of good y. So ym is equal to m over py, and if they are equal, so then this means that consumption of good y could be anything between 0 and m over py. So this is the case where the difference curves are linear, so that their marginal rate of substitution is constant. Then you have to see that whether the budget constraint is flatter than the indifference curves, or whether it is steeper than the indifference curve, and then on that basis you will be writing down the equations of the Marshall demand functions. Alright. This is the second question for the utility function u equal to x to its power 0.2 y to its power 0.8. Derive the corresponding true cost of living index. So see that I have done it using the minimization problem. So here, minimize these expenditures subject to the utility constraint. Whenever you are given this type of function and you are being asked to find out the Martian demand function, or like for example the true cost of living index or Hicksian demand function, my advice to you is that in place of using these 0.2 or 0.8 or any other powers that are given, use alpha and beta. Make sure that you are, if alpha and beta are such that alpha plus beta equals to 1, then this is something that you will be able to make use of later on. See that when you solve this problem using the Lagrangian multiplier, you will do it by yourself to obtain the Hicksian demand functions. So this is the Hicksian demand function for good x, and this is the Hicksian demand function for good y. And I plugged these Hicksian demand functions into this expenditure equation here in place of y and in place of x. And when I did that, I was able to get this expenditure function E equal to 1 over alpha raised to the power alpha, beta raised to the power beta, px raised to the power alpha, py raised to the power beta, and u bar. So this is the expenditure function. Then we know that the true cost of living index is equal to expenditures to attain a particular utility level with current prices divided by expenditure to attain the same level of utility at base year prices. So see that here I have put this C to indicate this is the current price, C this is the current price, and this is the base year utility U bar, and I have 1 over alpha raised to power alpha beta raised to power beta times px c, current price of x raised to power alpha, current price of y raised to power alpha, and base year utility divided by 1 over alpha raised to power alpha beta raised to power beta, px base year price raised to power alpha, base year price of y raised to power beta, base year utility. Now what will happen is that these utilities will be cancelling out. Similarly, these will be cancelling out, and I will be getting it equal to px c raised to power alpha, py c raised to power alpha divided by base year price of x raised to power alpha multiplied by price of y, base year price of y raised to power beta. And whenever current prices and base year prices are given to you, you can find out these true cost of living index. See that if you recall that xm actually is equal to uh, alpha m over px for this utility function, and ym is equal to beta m over py for this utility function. And if you plug these Marshall demand function rather in the budget constraint, so you get m equal to um, um, px x, and in place of x write down the Marshall demand function here like this, px, and similarly write down the Marshall demand function for y here, py uh, beta times m over py. So if you do this, see that px get cancelled and py get cancelled, and you get m equal to alpha plus beta. What is alpha and what is beta? See that if I write down the equation px x divided by m, suppose that I write down this. So this is your expenditure share, share of income being spent on x. In this equation, put the demand function alpha m divided by p of x divided by m. Then px will get cancelled, m and m will get cancelled, and you will be getting alpha. So alpha actually is the share of income going into the consumption of x. Similarly, beta is the share of income going into the consumption of y. So like for example, if this is equal to 0.4, then this must be equal to point here there was an m, and we get alpha plus beta equal to 0.4 plus 0.6 equal to 1. So m equal to px alpha m over px plus py beta m over py gets cancelled, px get cancelled. Here we are left with alpha m, here we are left with alpha beta m. So I take m out. So on the left hand side I have m equal to alpha plus beta times m gets cancelled, and I get alpha plus beta equal to 1. Alpha I have shown you is the share of income being spent on x, beta is the share of income being spent on y, and to the sum of these shares should be equal to 1, that is vacanted. So this is something that is an additional dimension of this problem. But then remember that this is the true cost of living index, the answer to the question. Alright, then we have this elasticity form of the Slutsky equation, which we now need. So the question is that how to find out the elasticity form of equation. This computer is not working efficiently. So see that this is the Slutsky equation. What I have done is that I have multiplied this Slutsky equation by px over xm. Px over xm and xh are equal at optimum, so I could put xm or xh, so I have preferred to put xh and see that px over xm. So I multiplied this entire Slutsky equation by px over xh and px over xm. Remember that I am making use of the fact that at tendency point xm is equal to xh. But then see that this is the Marshallian elasticity. So I have this Marshallian elasticity. This is the Hicksian demand elasticity. So I have this income Hicksian demand elasticity. Then minus comes here, and see that in addition to multiply this last term by px over xm, I have divided and multiplied it by m and m. And when I did this, so see that I am having this part which is sorry this part. Let me take another pen. So consider this part along with this part. So this is dava x over dava m times this m divided by this xm. So this is income elasticity, and what is left is px xm over m. So px xm over m is the share of income being spent on x. So this is x here. So this is the elasticity form of the Slutsky equation. Alright, then use the example associated with figure 8.3. This was the text example where they had shown in figure 3.1 the uh, implication of a sales tax. So let me first clean this um, a little bit. I want to I cannot do it. Alright, this is slow, a little bit slow. Let me okay. My computer actually is not working well. So see that this is not moving alright now. Okay. Now see that this is your initial budget constraint, and your okay. This is your initial budget constraint you are consuming here. A tax is imposed on consumption of good X. So your price of good X increases because of the consumption excise tax on X, and this becomes your budget constraint. And see that on this budget constraint you are consuming here, you are consuming say x1 units of good 1 good X, and y1 units of good y with tax. Now ask the question that if tax had not been there, and then if you had been consuming x1 units of good x, what could have been the amount of good y that you could have consumed? So see that if tax had not been there, then the initial budget constraint would have allowed you to consume y2 units of good y, but because of tax you are consuming only y1 units of good y. So this means that this reduction in consumption of good y is because of excise tax. So we are measuring excise tax in terms of units of y that you cannot consume after the excise tax is in place. The amount of tax is this vertical distance. Then we ask the question, okay, what if in place of using an excise tax we use an income tax? If we use an income tax, then this means that this budget constraint will be shifting inward without changing its slope, and when this happens, then we will be like having this budget constraint uh, passing through this point of excise tax C, and so after this income tax has been levied, see that we still have the same amount of tax. The budget constraint has shifted inward in a parallel fashion, and so see that because of this vertical distance actually now is representing the amount of income tax measured in terms of units of y, but because these two budget constraints are parallel, so this means that this distance is equal to this distance is equal to this distance and is equal to this distance, and so this means that this is the amount of tax. But after income tax C, we have the opportunity to consume at a point like this, which is lying above this utility level which is available after excise tax. And so see that if the consumer consumes here, so the tendency points will be occurring at this point, and so see that with income tax utility will be falling from u2 to u1 if the same revenue is collected using excise tax or sales tax. Your utility falls from u2 to u0, and so loss in utility in excise tax is more than the loss in utility due to income tax. It is because of this reason that people argue that income tax is a better way of collecting sales tax, because in both taxes you are collecting the same amount of revenue, but in terms of utility the burden on the consumer is less in terms of it's less with income tax relative to with excise tax or sales tax. And the reason that this is happening is hidden in the substitution effect. See that this point is representing a sort of substitution effect with respect to this point, the Slutsky substitution effect. Now if the preferences are Leontief like this thing, so see that in this case the income tax and the income tax and the excise tax result in the same loss of utility. So if there is no substitution effect, the loss in utility is the same. And remember that this additional loss in utility that we are seeing here, u1 minus u0, is known as the excess burden of the excise tax or excess burden of the indirect tax. So whenever substitution is there, then associated with any tax policy, then that tax policy will be imposing an excess burden or social welfare loss, which is not existing if the two goods had been perfect complements or the preferences had been of the Leontief type. So this is something that I had asked to tell you. This was something that was given in the text, and if you replace the indifference curve with the Leontief indifference curve, you will see that both income tax and the excise tax becomes equivalent in terms of utility loss. It is for this reason that it is often claimed that if goods are perfect complements, then income tax and excise tax have the same loss of utility, so no excise burden associated. This is an old paper actually that is coming from 1939 by Little that this conclusion was drawn. So this was question number 5. Okay. Well, question number 6, for the utility function given in equation 3, check whether goods X and Y are gross substitutes or gross complements, whether they are net substitutes or net complements. See that this was the action demand function, and in that question number 3, and I have taken the derivative of the action demand function with respect to price of Y, and if you look into this result of this derivative, beta is greater than 0, py is greater than 0, this term is greater than 0, and this is something that is saying that this derivative is greater than 0. And because this derivative is greater than 0, then this means that when price of Y increases, consumption of good X increases, so good X is a net substitute, so the derivative is greater than 0, so we have a net substitute. So remember, how will you be doing that? You first will be writing down the action demand function, and then you will take the derivative of the action demand function with respect to the price of the other good, and if this derivative you are able to prove is greater than 0, then this means that the two goods are net substitutes, and if you are able to prove that the derivative is less than 0, then this would imply that the two goods are net complements. We have also seen that in the two good world, the goods are necessarily net substitutes, so necessarily this in two good case, this is something that is going to be greater than 0. Alright, then what about the gross complement or gross substitutes? See that for this utility function, this is what that we have: xm equal to alpha m over px is the Marshall demand function. If I take the derivative of this Marshall demand function with price of with price of y rather, is here Marshall demand function with price of y, because see that in Marshall demand function there is no py, so this means that the derivative of Marshall demand function with price of y will become equal to 0, and this means that the two commodities are neither gross substitutes nor they are gross complement. If you had a Marshallian demand function for which this derivative had been greater than 0, then we would say that the two goods were gross complements. If gross substitutes. If for the two goods case, for example, you had a Marshall demand function for which this derivative was less than 0, then you would conclude that the goods are gross complements. So whether the goods are gross substitutes or gross complement, to check this you need to take the derivative of the Marshall demand function for the good with respect to the price of the other good. If you want to check whether the good is a net substitute or net complement, you need to take the derivative of the Marshall demand function of that good, the derivative of the action demand function of that good with respect to the price of the other good, and then you will be able to conclude on the basis of the sign of the derivative here or here that whether the goods are net complements or net substitutes. So this is the fifth question that we had, and then we have here the Cobb-Douglas production function that has been given here, and then we are asked to check whether the function exhibits increasing returns to scale or constant returns to scale or decreasing returns to scale. See that in order to do that, I have increased labor and capital in the same proportion, say lambda equal to 1.2. So 1.1 will mean that labor is increasing by 1% by labor is increasing rather by 10%. Similarly, if I multiply lambda by k by lambda, so this will mean that suppose that this is 1.1. So 1.1 L is greater than 1 L, 1.1 K is greater than 1 K. So this, if it is equal to 1.1, then this means that I have increased labor by 10%, I have increased capital by 10%. So what is going to happen to the output? This is the question. So when now I open these brackets to lambda raised to power alpha, L raised to power alpha, lambda raised to power beta, k raised to power beta to lambda raised to power alpha, lambda L raised to power alpha, lambda raised to power beta, k raised to power beta. Then I added the powers of lambda to become lambda raised to power alpha plus beta, L raised to power alpha, k raised to power beta, but L raised to power alpha, k raised to power beta is equal to q, so I have plugged q here, lambda alpha plus beta raised to power alpha plus beta. Now if alpha plus beta is equal to 1, then we will be having q star equal to lambda q, indicating that if all the factors of production are increasing by 10%, so this means that output is also increasing by 10%. If alpha plus beta is greater than 1, so this means that uh, Q will be increasing more than 10%, and if it is less than 1, then this means Q will be increasing by less than 10%. So it will all be depending upon what is the power of lambda. If it is equal to 1, then this means that we have constant returns to scale. If it is greater than 1, then it will mean that we have increasing returns to scale. If it is less than 1, then we have decreasing returns to scale. And then see the part B is that we want to find out the ranges of employment that correspond to the first, second and third stage of production. Now, because it has already been mentioned that this is a Cobb-Douglas production function, and strictly speaking, for Cobb-Douglas production function, we have alpha plus beta equal to 1, alpha greater than 0 and beta greater than 0. And see that from class we know that the first stage of production is the employment of labor from 0 to LA, where LA is the employment of labor at which average product of labor is at its maximum. That the second stage of production is where the employment of labor is LA, at which the average product of labor is at its maximum, to LM, where the marginal product of labor has become equal to 0. And then we have the third stage of production, which is like saying having employment greater than L of M, because it is greater than L of M, so this means that marginal product should be negative. So these are the stages of production. Now see that because we are talking about the total product of a particular factor of production, in terms of stages of production, say labor, so we have to keep capital constant, so I put a bar here, and then what I have done is that I am saying that let it be equal to a constant C, so that your total product of labor becomes C times L raised to power alpha, just to write it cleanly. Then I define the average product of labor. Remember that average product of labor is total product of labor divided by labor, and when you do it, it is C L raised to power alpha divided by alpha by L, and this is equal to C L raised to power alpha minus 1. So C L raised to power alpha minus 1. Now I take the derivative of average product of labor with respect to labor, and this derivative is this power comes down, C is at its place, and from the power of L I have subtracted 1, to L is to power alpha minus 2. Now look into this average product of labor curve. If alpha is less than 1, so greater than 0 bar. So then this means that this number actually will be less than 0, and this means that this is less than 0, and if it is less than 0, so this means that average product of labor is continuously falling. Labor here, average product of labor here. And if it is continuously falling, so this means that marginal product of labor is here. And in the complex production function, this is the case for any employment of labor. So this means that we are in the second stage of production. This is something that you need to keep in mind. Strictly speaking, for complex production function where alpha plus beta is equal to 1, so we only have second stage of production. Because alpha is less than 1, so this means that it has to be negative. This derivative has to be negative. For this derivative to be positive, alpha must be greater than 1, and if alpha is greater than 1, then this means that average product of labor is rising. So this is not the case with Cobb-Douglas production function. So just to keep in mind that in the case of Cobb-Douglas production function, we have average product of labor falling as well as marginal product of labor falling. It is never increasing, so we don't have first stage of production. Similarly, the average product of labor will never be becoming equal to 0 for any level of employment of labor. Similarly, margin product of labor will never be becoming negative or equal to 0. So it is universally true for the Cobb-Douglas production function that for any employment it is only exhibiting diminishing marginal productivity as well as diminishing average productivity, which corresponds to the second stage of production. Then I have solved this for the this was the tedious one. See that we needed to find out the factor demand function for the Cobb-Douglas production function. In order to do that, see that I first wrote down the profit equation, which is like let me get pen first. All right. So my computer has gone tired for some reason. Not working. It is stuck around here. So see that this is something. Alright. This is not coming in. Alright, I have okay. Alright. So see that I had this profit function. It is totally not working now. Tired. Okay. So this is the profit function. See, P times profit actually is equal to P times and this is totally not working. Let me reset it and then we'll start again. Alright, let's restart. I will not edit this presentation because I do not trust my machine. I will try to see that I have uploaded this presentation as quickly as possible before my machine goes out of order completely. So if There might be some confusion, but then try to understand the question and their answers as closely as possible. Alright, this was the question that we were talking about, the factor demand functions. See that we had this uh, profit equation seen in our class. It was like f of labor and capital and minus WL minus RK, and in place of this um, production function, I have inserted this Cobb-Douglas production function that has been given in the exercise, and see that then I take the partial derivative of this equation with respect to labor first and equate it to 0, partial derivative with respect to capital, and then I equate it to 0, and then I take this W on the other side in equation 1 and this R on the other side in equation 2, so this becomes equation 3 and 4, and then I divided equation 3 by equation 4 and see that this was the result, and I solve it for L. So L was like equal to alpha over beta R divided by W times K. Then in the next step I plugged this value of labor in equation. You could plug in equation 1 as well. I plugged it in equation 2, so see that equation 2 is beta here, and then I have price which is here, and then L raised to power alpha. In place of LC that I have used this value, and raised to the power alpha, K raised to power beta minus 1 is here, and minus R has been taken on the other side to become plus R, and then I simplified this a little bit, so opened the bracket, so this beta is as it is, P is as it is, see this was alpha, and this is alpha is coming here, so alpha raised to power alpha, beta raised to power alpha, so this alpha is coming here on this power as well as on this power and everyone where, so R raised to power alpha, W raised to power alpha, and finally I have K raised to power alpha. That is, I have opened this bracket, and then this K raised to power beta minus 1 is at its place, and then I have R. Then I have taken everything else on the right hand side, so see that this is something that is coming here in the denominator of R, and that this term actually is getting inverted, beta over alpha raised to power alpha in the numerator and alpha raised to power alpha in the denominator, W raised to power alpha in the numerator and R raised to power alpha in denominator. So make sure that we have all the elements here. Then I have simplified it in a particular way. See that K raised to power alpha plus beta minus 1 is still on the left hand side, but the next step I have taken all the denominator into the numerator. So see that this was P in the denominator, and when I took it into the numerator it became P raised to power minus 1. Similarly, beta was in the denominator, I took it into the numerator to become beta raised to power minus 1. Beta raised to power alpha was already there, and I take alpha raised to power alpha up to become alpha raised to power minus 1, and the same is true for all the other entries. And then see that I little bit rearranged this b raised to power minus 1 as it is, but I had b raised to power minus 1 here, b raised to power alpha here, so b raised to power alpha minus 1. Similarly, I have alpha raised to power minus alpha at its place, and w raised to power alpha at its place, and see that I had r here and r raised to power minus alpha, so I added the power so that I have now r raised to power 1 minus alpha. Then I like divided by power by alpha plus beta minus 1, and when I did this, see that I was able to get k here, every power. I divided this power by alpha plus beta minus 1, and I did with every other power, because whatever we are doing on the left hand side we should be doing on right hand side as well. And when I did this, I was able to get this uh, factor demand function for capital, and similarly factor demand function for labor. Now see that the once you have obtained one of the factor demand function, like for example I obtained for capital, and then the other factor demand function was obtained by symmetry. So everywhere in place of beta I have plugged, I have substituted it by alpha. So see that I had alpha here, alpha minus 1 here, I have beta minus 1 here. So this is something that we will be able to get directly through manipulation or resolving for k star. Once you have obtained this k star, you can go back to this equation and you can plug k star here, and then you can solve for the factor demand for labor as well. And this is something that we are able to get here. So factor demand function for capital, factor demand function for labor. I will suggest that you should keep this presentation in front of you and try to solve it by yourself. Now, what restrictions you will be putting on on this production function q equal to L raised to power alpha k raised to power beta. Well, one important restriction that you need to put on this production function is that alpha plus beta should be less than 1. And if you don't do that, you actually will not be able to get the factor demand function correctly, or you will not be able to get the factor demand function at all. Why? Because you see that alpha plus beta is equal to 1. So this will become equal to 1, and 1 minus 1 will become equal to 0, and anything divided by 0, this will become minus infinity. And so this system actually will be exploding, because alpha plus beta minus 1 is in every denominator in the power. So this means that the system will be exploding and you won't be able to get neither k star nor L star. So this is one thing, that alpha plus beta should not be equal to 1, but it should also not be greater than 1. Why? Because if it is greater than 1, then this means that it will be becoming positive, and if it becomes positive, then we will be having, for example, double over double w greater than 0. We had seen that this should not be the case. If profit maximizing conditions are satisfied, we know that the factor demand function should be downward sloping, so this should actually be the case. So if it is greater than 1, then we will be having this derivative double star divided by double w. See that all these things will remain at their place, and see that we will have this thing coming down, and we will be having w raised to power this thing minus 1. And if this thing is positive, so this means that this derivative will be becoming positive, and then you will be getting a wrong sign for the labor demand function. And in order to make sure that this is not happening, you have to ensure that alpha plus beta actually is less than 1. So this is the other thing that you need to keep in mind. Now, as far as this last question is concerned, I have already written it that this is a solve example on page 56 of variant, and solve example of this part B actually is the solve example of in variant on page 57. So that is something that you'll be able to see by yourself. So I hope that this might be of some help to you for a while to understand these quiz app problems as well as these homework problems. So let me upload it as quickly as possible, so that before my computer breaks down completely. Uh, there will be some troubles, some noises, etc. But the thing is that I'm not going to edit this video, because I'm not willing to take any risk any further. So rest is up to you. Thank you.